Okay, so it's a great pleasure to have Alex Perry, currently from the IIS, and he's going to tell us about stability conditions and cubic fourfolds.
Yeah, that's right. Okay, thanks a lot for the invitation. Yeah, so eventually I'll talk about stability conditions, but first I'll just say a little bit about cubic fourfolds and their derived categories. So in this whole talk, I'm going to work over the complex numbers, and throughout the talk, I'm going to fix x in P5 to be a smooth degree 3 hypersurface, so I'll call that a cubic fourfold. Okay? And so the starting point for the things I want to tell you about today are some results by Kuznetsov. So I'm going to summarize these results in like a theorem with a couple parts. Okay, so the first part of the theorem is sort of a structural result about the derived category of this thing. So d of x, let me write it like this. There is a semi-orthogonal decomposition of the derived category of x. So in this talk, I'll just write d of x to mean the bounded derived category of coherent sheaves on it. That's my notation for it. And this thing has a semi-orthogonal decomposition that looks as follows. So there are three sort of simple cases. There's O of x, O x boosted by 1, and O x boosted by 2. These are simple conjecture states. So there's two line bundles, and then there's an interesting piece. any variety y. Okay. Yeah, so to summarize, we have this canonical subcategory. Homologically, it looks like a K3. Sometimes it is a K3, but generically it's not. And actually, I sort of have to mention this really beautiful conjecture that motivated a lot of this work that Netzov made. So we made the following conjecture. He conjectured that this condition appearing in 3 exactly encodes the rationality of the cubic fourfold. So he conjectured that cubic fourfold is rational. So X is rational, meaning birational to T4, if and only if this condition holds. So Q of X is equivalent to D of S, where S is a K3. Okay, so this is like a really striking conjecture. I mean, a priori, there's no reason for rationality to be related to the structure of the derived category. Nonetheless, there is some evidence for it. Like, for instance, Faustian cubics are rational. So this part 3 is like an example of checking this implication in a special case. And there are a couple other known families of rational cubic fourfolds. And for those ones, this implication has been checked. But in general, I would say it's like a pretty mysterious conjecture. Maybe I can make two remarks about this. The first remark is that, like, both implications, let me make a remark about each implication. The forward direction is very strong. Combined with part 4, it says that a very general cubic fourfold is not rational, which is like a big open conjecture. The converse implication is also really strong. So there are only a couple known constructions of rational cubic fourfolds, but it turns out there are many examples of cubic fourfolds with an equivalence like this. So this backwards direction is predicting there should be many rationality constructions. We don't know that.
How does this relate to these passive families?
That's a good question. So later in the talk, I'll say the answer is that they're exactly the same, but I'll say something about that later. Okay. Any other questions? Okay. So eventually, I will come back and say a little bit more about this conjecture. But the first goal, yeah.
If the condition does what clear that S has to be a K3 or the generation of K3?
It actually, if Q is the variety, it has to be a K3, and that's relatively easy to check. You just like look at the Hochschild homology, and you can deduce it has to be a K3. So yeah.
So with the transcendental lattice of X, it has morphed to some transcendental lattice of K3, then you can conclude that
I think at least generically that's true. So it does translate. You can translate this into a Hodge theoretic condition, and then at least in some cases, I think that would be but maybe later I'll get back to describing the Hodge theoretic. So the main goal of this talk actually is to sort of run with this idea that Q of X looks a lot like D of a K3, and the idea is that we should do things for Q of X that we can do for K3 surfaces. So one really nice thing about K3 surfaces is that they have well-behaved moduli spaces of sheaves. And so the goal of this talk is sort of to describe an analog of that for Q of X. So we want to understand moduli spaces of objects in this category. And so to do that, the technical sort of tool for thinking about moduli of objects in a category is bridge instability. So I'm going to give like a quick review of bridge instability and the main things that we need for this talk.
Do you have an intrinsic definition of class of categories that look like Q of X?
You can.
Or do you only get them out of Q4?
No, there are some other ones. Actually, at the end of the talk, I might write down a couple other examples, but you could say, like for instance, you could say it's a category, a triangulated category, which has a serofunctor that is shifted by 2, and then you might impose that its Hochschild homology looks like the Hochschild homology of a K3 surface. So that would be one sort of abstract definition of a K3-like category. And there are other examples, but again, maybe if I have time, I'll write that some examples as well. Okay, so let me tell you a little bit about bridge instability. And it's going to be sort of a quick review. I'll just tell you the key points that you need to know for this talk. And so we're going to look in the following setting. I'll take D to be a semi-orthogonal component of D of a variety where Y is smooth and projected. And so, for instance, you could just, if you want to, for this whole discussion, you could think of D being proof X. Okay, but it makes sense more generally, this discussion of Bridgman stability. And so, first I want to observe that there's a natural bilinear form, which is given as follows. So I'll call it E paired with F. And it's given by the alternating sum of the dimensions of the X groups between E and F. So this is a form, a bilinear form on what's called the Grothendieck group of this category D. So by definition, the Grothendieck group is just the free abelian group on isomorphism classes of objects in your category, modulo the relation that if you have an exact triangle. So in a triangulated category, there's a notion of exact triangles, which is like a generalization of an exact sequence. And whenever you have an exact triangle, we're going to declare that the class of E is the sum of the class of A plus the class of B. Okay, so this defines some abelian group canonically associated to D, which is called the Grothendieck group. And this thing is a bilinear form on it. And actually, just for some technical reason, I'm going to use minus of this Euler of this form. Okay. And so now, in general, this Grothendieck group can be sort of humongous. It's comparable to the size of the Chow group of your variety, if D is like D of your variety. So we're going to work with something a little bit smaller, called the numerical Grothendieck group. So let me just define that for you. So the numerical Grothendieck group I'll denote by n of D. And by definition, it's just the usual Grothendieck group modded out by the kernel of this bilinear form we just defined. So one way I could write that is modded out by the orthogonal to the elements that came out of D. Makes sense? So I just quotient by the subgroup of all elements whose pairing with every other element is 0. Okay, so sort of numerically trivial. And this thing, this is always a finite rank abelian group. I mean, it's even a lattice. It still has that bilinear form on it. Okay, and so yeah, and actually, I work in the setting of D being a component of D of a variety. But for the discussion of Bridgman stability, all you really need is that this expression should make sense. So in other words, the direct sum of all these x should be finite dimensional, and we need this as an assumption too, that this thing has finite rank. But these two things follow automatically when your category is a semi-orthogonal component of D of a variety. Okay, so this is sort of the starting point to tell you what a Bridgman stability condition is. So let me define it for you, or at least roughly define it for you. So a stability condition. So more precisely, what I'm going to define for you is what's called a numerical stability condition. And it consists of the following data. I'll call it sigma, and that's a pair of something called A and something called Z. So MD is the following. So the first thing that we have is this piece of data A. So A inside of D is supposed to be the part of a bounded key structure. Okay, so instead of giving you the completely technical definition of what this is, let me give you the canonical example of a heart of a bounded key structure. So for example, e.g., you could take A to be the category of coherent sheaves inside of D of Y. So this is the case where curly D is actually D of a variety. And then coherent sheaves form an example of this kind of thing. So in words, what are the, so this notion, it abstracts the properties that co-inside of dB of Y has. Namely, A should be an abelian subcategory of D, and every object in D should be able to be broken into finitely many cohomology objects that lie in this abelian category A. That's exactly how dB co is, right? Every object in dB co, by definition, has finitely many cohomology pieces, which are coherent sheaves, and coherent sheaves are an abelian category. So it's a way to break your triangulated category up into pieces that lie inside of an abelian category. So maybe that's what I'll say about this first ingredient. You need a Hart with a bounded T structure. And the second thing that you need is this thing I call Z. So here, Z is a homomorphism from this numerical Grothendieck group to the complex numbers. So this is an additive homomorphism such that the following property is satisfied. So such that if you have any object in D, you can consider its class in this numerical group, right? You can just look at its image in this group. So the condition is that if you take any non-zero object in this Hart, A, then it should lie in a special subset of the complex plane. It should lie in the strict upper half plane union the strictly negative real line. So pictorially that looks as follows. So if you take Z of any non-zero object in your Hart, it should lie in the upper half plane union the negative real line. Okay, so that's this is the condition on Z. So for example, let me just give you an example. E.g., you could take Z to be minus the degree plus I times the rank in the case where Y is a curve. And I'm using for the Hart this one from our previous example. So if you have a curve, right, if the rank of a coherent sheaf is 0, then the degree is positive. So minus the degree is negative. Okay? And to write down examples in higher dimensions is actually quite a hard problem. But let me just tell you in dimension 1. Okay, so that's almost a complete definition. Let me just say you need those two pieces of data, plus you need them to satisfy a couple conditions. But these conditions, I'm going to omit the description of them in the talk. In words, you basically need what's called a Harder-Narasimhan filtration, and you also need a technical thing called the support property. But for the purposes of this talk, I'm going to maybe not talk about that. I won't consider this one. Okay, let me tell you the the key upshots though. Like what do you get if you have a stability condition? Call these maybe the key points. Okay, so the first key point is that when you have a stability condition, there's a natural notion of stable and semi-stable objects in this abelian category. So sigma induces the notion of stability. So more precisely, if I give you a non-zero object E in this category A, then I'll say that it's stable or semi-stable if the following condition holds. So whenever you take a non-trivial subobject, say F, inside of E, I want the following inequality between the slopes to happen. So I want the slope of f to be either less than or equal to, in the case we're defining semi-stability, than the slope of E. So here, the slope is the following quantity. So it's something determined by the sigma, and by definition, it's minus the real part of Z of E divided by the imaginary part of Z of E. Okay, so this might look a little bit strange at first, but for instance, if you think about it in this example here, what we're getting is the usual slope stability of sheaves on a curve. You're getting the slope is the degree divided by the rank. Okay, and so this you can think of Bridgeland stability roughly as sort of a generalization of slope stability on curves to arbitrary categories. Okay, so we have notions of semi-stable or stable objects with respect to sigma. And the reason that's important is what I'll call key point 2. And it says the following. So let's say that we fix some element in this numerical growth medium, call it B. Then we can look at moduli spaces of objects which are semi-stable of class B. So let me say it like this. We can consider M sub sigma of B the moduli space of sigma semi-stable objects E in this category A, such that the class of E is equal to B in this numerical growth medium. Okay, so basically, you know, if you didn't have the stability condition, you could say, let's just look at the moduli space of all objects of a given class B. And the point is, if you do that, you just get terribly behaved spaces. So it's similar to the reason that you need, you know, a notion of stability to form well-behaved moduli spaces of, say, sheaves on a curve. For the same reason, you need some kind of way to cut down the space of all objects to get a potentially well-behaved moduli space. So that's the idea behind Bridgeland stability. So now for any vector, you can at least define a functor. And technically what I mean here is M is supposed to be a coarse moduli space for the natural functor parameterizing semi-stable objects in class B. And in good cases, you could hope to prove that this thing exists, that there is actually a coarse moduli space, maybe that it's projected, and things like that. So I'll give you an example where you can actually prove things like that in a minute. But so this is maybe the main upshot of Bridgeland stability. And the third thing, which is nice, is that the set of all stability conditions, which I'll call stab of D, this thing is a complex manifold. And it has dimension equal to the rank of the numerical growth in D, at least if it's non-empty. Okay, so these stability conditions, they have a nice property, which is that there's a good deformation theory of them. So once you have one, you have many of them. You have a whole complex manifold with that. And the dimension is exactly the rank of this group. Any questions about this? This is my summary of Bridgeland stability. Okay, well, I'm going to tell you what, like, the statement of some theorems now in the case of Q of X for this category associated to a cube. Yeah, and so this question of whether or not there exist stability conditions, in other words, whether that stability manifold is not empty, is like a notoriously hard problem. So in dimension, if D is the derived category of the surface, then we know that there are stability conditions. If it's a threefold, nowadays we do know in a lot of cases, but definitely not in general. We're far from knowing in general if there's stability conditions. And for higher dimensional varieties, the situation is just even worse. So it's really hard to construct these things. And the starting point for the main theorem I'm going to tell you about today is a theorem about the existence of stability conditions. on that category Q. So this was a theorem proved by Fire, Lahose, McCree, and Scolari. So what they showed is that that stability manifold is not empty in the case of the Q of X. This tab of Q of X is not empty. Okay, so for the purpose of this talk, it won't be so important to tell you exactly what that stability condition is. It's actually quite hard to write down the stability condition in. But let me just say, in particular, because of this statement I was telling you that there's a whole complex manifold worth, since they showed it's not empty, you get at least a component of the whole Bridgeland stability manifold containing the point they construct, and I'm going to call this component stab dagger. So stab dagger of Q of X is the corresponding component inside the field. Component of stability manifold. Okay, so we get a whole manifold's worth of stability conditions, which I'm calling stab dagger. Okay, and so now I can tell you what the main theorem of the talk is. So this was with these guys, E, L, M, and then also me and Howie Newer. Okay, so these are the people who did it, and the theorem tells you exactly what moduli spaces of objects look like. So there's M sigma V, when sigma is in this stab dagger. So let me write it down. The statement is a little bit long. Can you see this part of the board? This part's okay. Okay, so let me first tell you the input to the theorem. So you need to start with the non-zero vector V in the numerical growth indeed group of Q of X. And I'm going to assume that this vector is primitive. So in other words, it's not divisible. It's not a multiple of any other class inside of it. Okay, so start with the non-zero primitive vector in the numerical growth indeed group in this category. And also, I'm going to fix sigma in stab dagger of Q of X. So this is a stability condition, and I want to assume that it's generic with respect to V. Generic with respect to V. So this means something precise. So what it means is that if you look at an object of class V, then it's stable if and only if it's semi-stable. So, and it's a fact that these always exist. You can, given a fixed vector, you can always find a sigma which is generic in the sense that these notions of semi-stability and stability coincide for objects of class V. So this is the data we fix. Okay, you fix V, then you can always find such a sigma. A generic sigma will have this property. And then the theorem is the following. So M sigma V is a smooth projective hyperkähler variety of dimension V paired with V plus 2. So this is the pairing that we always have on, this is the pairing from before on the numerical growth indeed. And moreover, this thing, M sigma V, is deformation equivalent to Hilbert's scheme of points on a K3 series. Okay, so let me make some remarks about this. First of all, maybe I should say what I mean by hyperkähler in this talk. So smooth projective hyperkähler means that pi 1 is trivial, and also the space of polymorphic two-forms is spanned. It's one-dimensional, and it's spanned by a two-form which is symplectic. Okay, that's the definition of a hyperkähler variety in this talk. So this thing is hyperkähler. Its dimension is given precisely by this quantity, and it's actually deformation equivalent. So there's a smooth family whose special fiber is a Hilbert scheme of points on a K3 surface. So Hilbert schemes of points on a K3 surface are like the classical example of hyperkähler varieties. So let me see. Let me make a couple remarks, and then a lot of the rest of the talk is sort of extracting some information from this theorem. So the first thing maybe I should say is that in the case where instead of Q of x you look at D of a K3 surface, this theorem, an analog of this theorem was known. So that was due to Yoshioka and Byron McCree like a number of years ago. And actually, the idea behind our proof of this theorem is like a deformation theoretic argument. In some sense, what you want to do is specialize your cubic fourfold to the case where Q is D of a K3 surface. We know what happens in that case, so then you'd like to perform back to a generic cubic fourfold there. And to do that, we actually developed sort of a lot of theory related to bridge instability and a family of varieties. So bridge instability, as I sort of defined for you before, is something about a fixed category, like D of a variety or a component inside of it. And the technical thing behind a lot of our work is developing a theory that works not for a fixed category, but a family of categories or varieties. So, but I actually won't say so much about the proof of this in the talk, and I sort of want to unwind it and extract some information. Okay. Are there any questions before we start doing that? What was it? Oh, they're smooth. Yeah. Okay, so yeah, so let me do, I guess you could call these applications. Okay, so the first application I'm going to tell you, in some sense, is just unwinding a little bit more explicitly what this theorem says. So the first observation is that for any cubic fourfold, there's always a rank 2 lattice, at least, of classes that you can pick this B pool inside. So more precisely, the A2 lattice embeds into the numerical Grothendieck group of Q of x for any cubic fourfold. And in fact, for a very general cubic fourfold, that embedding is an isomorphism. So, isomorphism for x very general. And I can tell you explicitly how you get this embedding of A2 inside of here. So it arises as follows. So let me call lambda 1 and lambda 2 the generators for this rank 2 lattice. So these things are explicitly given as follows. I'll explain what I mean by this in a second. Okay, so this is a structure sheet of a line twisted by 1 or 2. And I need to tell you what is this per thing here. So per, this category Q of x embeds into D of x, by definition is just a subcategory in there. And this thing which I'm calling per is the projection, or in other words, the left adjoint to that. Intuitively, you can think of it like orthogonal projection. You just take any object and you can peel off some copies of O, O1, and O2 to make it orthogonal to them in this category. So basically you take this object and you project it into Q of x, and then you take this object and project it into Q of x. And it turns out that they generate a rank 2 lattice whose intersection form with respect to this bracket bilinear form I told you about before is exactly this A2 lattice. And so now, in particular, in this theorem here, you can take V to be any primitive vector in the A2 lattice, and you'll get out of this a hyperkähler variety. Okay? And so this there are infinitely many primitive vectors in this rank 2 lattice, and their squares, V paired with V, is getting bigger and bigger. So in particular, what this gives you is infinitely many locally complete and even unirational families of polarized hyperkähler varieties. So let me say a little bit more explicitly why it gives you this. So what you can do is fix this vector V in A2. That vector, it makes sense on any cubic fourfold, because I told you there's a canonical embedding of this inside of numerical growth equal any cubic X. So now you can take this moduli space and you can vary X and form this moduli space. And what you'll get is a family of moduli spaces whose base is the moduli space of cubic fourfolds. The moduli space of cubic fourfolds is 20-dimensional. It's unirational, because it's parameterized by a big projective space that just encodes the coefficients of the polynomials. So over this 20-dimensional unirational space of cubic fourfolds, you get a family of hyperkähler varieties. And that's actually a locally complete family. So polarized hyperkähler varieties of K3n type, their deformation space is 20-dimensional. So you exactly get a locally complete family in this unirational. So people have been looking for examples for constructions of families like this for a while now. And before this, there was like 3 examples that are known, so maybe I can just review those for you. So previously, there exists only several such examples. Until 5:30, is that right? Until 5:30?
Yeah.
Okay, so the first one, which I think was maybe the first relation between cubic fourfolds and hyperkähler varieties, is what's called the Fano variety of lines on the cubic fourfold. So that's just the space parameterizing lines P1 that lie inside of your cubic fourfold. So this example was due to O'Toole and Ron a while ago. It's an 85. This example is from 85. So this is a hyperkähler fourfold. Okay, so this is a really beautiful example of a hyperkähler variety. It's a fourfold, and in terms of this description I just told you here, you can actually realize it as a moduli space. So it corresponds to the vector V, which is just lambda 1. Okay, and then indeed, if you do V paired with itself plus 2, you get 4. So at least at the level of dimensions, we'll have probably checks out. Okay, so the sort of smallest vector in there gives you the Fano variety of lines. Another example, more recently, was constructed by Len, Swerger, and von Straten. This was in 2013. So they constructed an example which is a hyperkähler eightfold. So the description of this eightfold is a little bit more complicated. It's constructed from the moduli space of twisted cubic curves on the cubic fourfold. But it's not quite that space, it's some contraction of that space. So it's a little bit more complicated to describe, but it's an eightfold. And in this language here, that corresponds to the vector v equals lambda 1 plus 2 lambda. And you can check easily that in this case, v squared is 6, so this number is 8. So again, it checks out the level of dimensions. Maybe just...
And they check that it's a locally complete family?
Say it again?
Did they check that it's a locally complete family?
Yeah, I believe it. And then there was one other example constructed from cubic fourfolds. So I'll call it O'Grady's exceptional example, which is a hypercalar tenfold. So O'Grady constructed this hypercalar tenfold, and then much more recently, like a few years ago, Radu Plaza, let me get the order. Saka and Blazon showed that you can interpret this in terms of cubic fourfolds, this construction. And in this language here, this corresponds to the vector v equals 2 lambda 1. Okay, and in this example there's a subtlety because this is not primitive, this vector. So actually the moduli space is singular, and the statement is that there's a symplectic resolution of that moduli space, which is this O'Grady. And I want to mention that the fact that you can interpret these in terms of these moduli spaces, that's not obvious. So that's something that was worked out by Lee, Bertuzzi, and Zhao. Okay, this one hasn't appeared yet, but I think it will appear soon. But the basic idea is that, like, if you have a line, you can project the structure sheet of the line into the category, and that's essentially the correspondence between lines and objects in the Rule. There's sort of a similar thing here in this example. Oh yeah. So you get a family parameterized by the space of cubic fourfolds. You get a family of hypercalars over the moduli space of cubics just by varying the cubic. You vary the cubic, and for each cubic you do this construction. And the moduli space of cubic fourfolds, that's unirational because it's dominated just by a big projective space, by the the space of all the cubic elements.
You never need to make any choices, just a cubic.
You just need the cubic, yeah. I mean, okay, so technically, if you really work this out, you only get it over an open subset of the moduli space of cubics. There's some subtlety with this genericity. I said you need to choose sigma generic with respect to B. So there is some subtlety. You really get this family over an open subset of the moduli space of cubics. But that's still good enough to get you rational.
Choose about the dimensions. So the dimensions stop, can it never go above 20?
The moduli space of these hypercalar varieties that you get, the smooth ones, when you do the smooth ones, those hypercalars, the polarized moduli spaces are 20 dimensions. Of the moduli, sorry, the moduli spaces of those hypercalars are 20-dimensional. The dimensions of these moduli spaces can go bigger. There are two moduli spaces, right? Yeah. So the dimensions of these certainly get arbitrarily large. You just take vectors of bigger and bigger self-intersection. That's why these dimensions are going up here. There's another moduli space, which is the abstract moduli space parameterizing those hypercalars. That moduli space is always 20. Does it make sense? Like the deformation space of these guys here.
This is where there's one.
No. Okay, let me try to say it one more time. So we have all these moduli spaces of objects in foo of x. Their dimensions vary depending on this vector v. But all of these hypercalars are hypercalars of K3n type. And K3n type hypercalars, at least their polarized deformation space, is 20-dimensional. That's all I'm saying. Okay, so let me say now the second application.
Over V is non-primitive to know. where you can perform this lengthy resolution?
No, I mean, that is known in the case of a K3 surface what happens. And I would expect, I think there should be basically almost no cases, except for this one where that happens. But I don't know if that's true. I would suspect that's true. Okay, so let me tell you about this second application. So this is application 1. Application 2 is to, it's related to that conjecture of Kuznetsov from the beginning. So let me say the theorem. So the theorem I'm going to write, there was a slightly weaker version of it. It was originally proved by Addington and Thomas, but we gave a different proof which is a bit stronger as a consequence of our work. So the statement is the following. So in Kuznetsov conjecture, we had this condition that there exists a K3 surface S such that Q is equivalent to D of X. So that's one condition. And this theorem says that that's equivalent to the existence of a hyperbolic plane inside of the numerical growth and decrease of Q of X. Okay, so let me tell you actually the proof of this. It turns out to be kind of easy if you accept the theorems from before. So here's the proof. So the downward direction is the easier direction. So the reason that this downward implication is true is that in D of a K3 surface, the rank 2 lattice spanned by the structure sheaf of a point and the ideal sheaf of a point, you can just compute that's actually a copy of the hyperbolic plane inside of the growth and decrease, the numerical growth and decrease of D of X. That's just a computation. So if these two are equivalent, then you get a copy of this hyperbolic plane inside of the numerical growth and decrease of the left-hand side. The interesting implication is the upward implication. Okay, so let's assume that we have this hyperbolic plane inside of n of Q of X. So literally what that means is that there exist vectors v and w in this lattice with the property that v paired with v and w paired with w is equal to 0, and also v paired with w is equal to 1. I just wrote exactly what it means to contain a hyperbolic plane. Okay, and so now let's take this moduli space. Let's consider the moduli space of objects of class V. So I'm going to call that S. Okay, so this thing, it has dimension v squared plus 2. So for us, that's 2-dimensional, right? Hypercalibride is a dimension 2 or K3 surface. So this thing is a K3 surface. This is a K3 surface. What was that? My definition of hypercalar was that there's simply one. Yeah, and that's part of the previous theorem. So these ones, so this is a K3 surface, and so I'm going to tell you why this condition holds for this X. Okay. So the reason is that there's a natural object in the derived category of the product of S with X. It's just the universal sheaf. So, I mean, this thing is a moduli space of objects in D of X, so there's some universal sheaf parameterized, living over this moduli space. And here there is some technical point. To have a universal sheaf, in general, all you have is a twisted universal sheaf. But to have an actual universal sheaf, that follows from the existence of a vector that pairs with V1. So if I didn't have that W, there would be some Brouwer class involved here, but there's a legitimate universal sheaf because I assume there's a W that pairs with V1. Okay, so we have the sheaf E, and you can consider the corresponding Fourier-Mukai transform from d of s to d of x. Explicitly, that just takes an object f inside of here and does the following. So first you do the pullback from S to the product, and then you tensor with this object E, and then you push forward to X. So here all of my functors are like derived functors, derived tensor product, pullback, and push forward. So that's what's called the Fourier-Mukai transform. So you get a functor from d of S to d of X. And the statement is that this induces an equivalence of 2 of x of d of s with 2 of x. So there's basically 2 ingredients for proving that. The first is that this actually lands inside of 2 of x. That's because this is parameterizing objects in 2 of x. So that sort of follows immediately. And then you need to check, it turns out to prove it's an equivalence, it's enough to show that it's fully faithful because you're working with these K3-like categories. And for that, you use an argument using that this is parameterizing stable objects. So there's some additional work to go here, but the main idea is just this. You get this canonical functor, and then you can check that it's an equivalence. Okay. What else do I want to say? Oh yeah, maybe I can make a remark about this question, how is this related to Hodge theory? So the remark is, and this is due to Hassett, or it follows from work of Hassett, that this condition appearing in the theorem here so that there exists a U in the numerical growth unit group of 2 of x. This cuts out a countable union, and even dense, it's a countable union of divisors in the moduli space of cubic fourfolds. So more precisely, if you're familiar with Hassett's work, he has a notion of a K3 surface being associated to a cubic fourfold. Roughly, that says that the primitive Hopf structure of the K3 is embedded inside H4 of the cubic fourfold, and that condition actually turns out to be equivalent to the existence of this hyperbolic. So, as a consequence of Hassett's work, it follows that this condition actually corresponds to an infinite union of divisors in the moduli space. So that's if you combine that with Kuznetsov's conjecture from before, that says something really interesting. So we now know that this condition here happens on a countable union of divisors in the moduli space. And Kuznetsov's conjecture, this direction of it, predicts that all of those cubic fourfolds are rational. So currently we only know that for like maybe 3 of those divisors. So there's a big gap between our knowledge of which cubics are rational and which ones aren't. And yeah, these moduli spaces of objects, M sigma V that we constructed, actually may be useful for understanding that question and some other ones about the geometry of cubics. So, a couple minutes left. Maybe I'll just say one last remark about this this theorem. Oh yeah, just to tell you sort of what the difference is between what we showed and what Addington and Thomas did. So Addington and Thomas showed this downward direction, which is the easy direction, but they also showed that this upward direction holds for generic cubic fourfolds in those countable unions of divisors. So in any divisor, those countable unions of divisors defined here, you can take a generic cubic fourfold in there, and they showed for a generic cubic fourfold, there is an equivalence like this. So the thing that our result fixes is how to specialize to the boundary of those divisors. And it sort of gives a different proof. Okay, so I think I'm pretty much out of time, so maybe I won't tell you about these other examples of K3-like categories. Thanks.
Can you elaborate on this comment about the Brouwer class? So if S wasn't, if you just took that moduli space, why wouldn't you have a universal shift there?
Well, if you look at the stack, it's like a gerb over the corresponding space, but you know,
I see. So they're stable, but there is a gerb there,
Yeah,
and that gerb may not be trivial.
might not be split, yeah.
I
And
see.
so this ensures that it's true.
I see.
So for instance, another way you could say it is, instead of saying a hyperbolic plane, you can replace this with the existence of a vector of square 0. And that's equivalent to having an equivalence with D of a twisted K3.
But you would know that the Kuznetsov component is twisted K3 in that case.
No, you will know. Yeah, what I'm saying is that here's a variation on this theorem, which follows by the same argument, that existence of a D of square 0 is equivalent to Q is equivalent to D of
Yeah,
S.
so you will prove that it is equivalent to a twisted K3.
Oh, I thought you said won't. Yeah, sorry.
No,
I
you-
didn't hear
okay.
Yeah, we will prove that, yeah.
Yeah, okay.
I mean, an example, the other example that people like are these infinite families, hyperparations, generalized primitives. Do they ever come up in these?
Yeah, that's an interesting question. So I don't know a way to make it fit into this. What you would want is you'd want like a family of categories which generically is not the even abelian surface, but for special ones it is. And I don't know any explicit families like that. By some kind of deformation theory, you can construct families like that. You can think of deformations of the category D of A, and there are deformations of that category which are not D of a given abelian surface, but it's a little hard to work with just an abstract deformation. To get a real handle on it, it would be useful to have categories like that embedded in some explicit drawing. And I don't know if there's such a. If there were, I think a similar situation.
But yeah, I mean, they don't necessarily have to be non-complete intersection embeddings.
You mean, oh, yeah, that's right. Yeah, so it's a little bit harder to imagine how to...
So you can imagine something like the Horus-Manfurt embedding working, but then you need to see what the formations were.
Yeah. Yeah, it's a little bit unclear.
Any other questions? Well, let's thank Alex again.
Thanks.